So Kepler's laws have a very interesting history. Kepler's laws. The first law. So the first law states that all planets orbit around the sun in an ellipse. Okay? Yes. That is the first law. Now, what that means is try to understand this. It's very important because it has a deep meaning. If you look at sun and let's say Earth, okay? Earth is orbiting around the sun in always this plane. You understand? The orbital plane of Earth is the same, it does not change. Okay? And the path also does not change for large amounts of time, for millions of years. This is the path. Got it? When you look at this, can you describe, how do you describe this motion? How can you describe this motion? You can describe this motion using your thumb and these four fingers. Okay. This is the motion, this is the plane. You understand? And Earth is moving like this. Okay. You got it? So this direction, okay, what is the, so this direction describes the motion itself, right?
We just want to talk.
Alright. So this direction, okay, or this the thumb itself describes the motion of Earth around sun. Right? What that means is, what happens if the plane changes? Does this direction change?
No.
If the plane changes,
The plane?
yes.
No, it doesn't. Plane changes, like
What is the relationship between this thumb and plane? Perpendicular, right?
Yes.
If the plane changes, does this direction change?
Yes.
It does change. It will not be perpendicular, right? Then you have to look at the that plane.
Yeah.
You got it?
Yes.
So this direction does not change. This direction is the angular momentum direction. That's what we have been talking about. Okay? The angular momentum does not change. Angular momentum is conserved, means this direction does not change. It is always doing this. You see that? Now compare this with, this is Kepler's law. Now this law, first law, was based on observations. Okay, observations for close to 10 years, 10, 20 years of observations. Okay, so this observation was by Johannes Kepler himself and his associate. I think I'm spelling it right. Or maybe Tycho Brahe. Okay, these two people made these observations for 10, 20 years and came up with this, the first two laws actually.
How do you say his name?
Tycho Brahe.
Tycho Brahe.
Yeah. Now you compare this with Newton's laws. Okay. Newton never did any observation to come up with his laws. Right? Did he do any observations with regards to gravity?
No.
The apple fell, but that did not indicate that the gravitational force was directly proportional to the sum of the square of the product of the masses and square of the distance. It just made him realize gravity. But when he proposed the law, it was purely based on intuition. And if you look at this, what is this? Look back in your notes.
What is that at the bottom of P naught?
H squared over mu.
That's mu.
Mu, yes.
That's H squared.
H squared. We discussed this in class yesterday. I gave you all these formulas.
Yes.
What is this? This is almost a direct consequence of Newton's laws. What this states is, understand why Kepler's first law is a special case of this. What does this state? This states that the trajectory, okay, so this is at R, right?
Yes.
Okay, this is at R. What Kepler observed was, he observed only planets, okay, and he and Tycho Brahe correctly predicted the path of planets to be ellipse. Okay. Now, if you look at the outcome of Newton's laws, it says this R need not be just an ellipse. It need not trace just an ellipse. It could trace circle, parabola, hyperbola. This is the equation of a conic section.
So it defines all possibilities.
It defines all possibilities.
Okay.
So that is the power of math and physics. They did this observation for 10, 20 years to come up with this ellipse. And there was so much hypothesis before that. Right? This was a result of mathematical, there is no observations here. This was a result of mathematical manipulation. Okay, so this Kepler's law is a special case of this, and understand why. What is the special case of Kepler's law? I gave you the 4 cases, okay?
It's only elliptical.
It's the elliptical.
Yes.
So the special case is when E,
Circular, hyperbola.
this is
Oh, when I haven't said this over.
Kepler's first law. You got it?
Yes.
Everybody gets this?
Yes.
Or you have difficulty getting this? E? What is the range of E?
From 0 to 1.
Oh, it's one and one.
Look at what I gave you. I gave you the range of E yesterday.
0 to 1.
Look at your notes.
0 to
Zero.
higher than 1.
0 to
It says higher than 1.
Infinity.
E can be greater than 1.
0 to infinity. Okay. 0 is what?
Circle.
So between 0 and 1, greater than 0, less than 1,
Ellipse.
ellipse. 1,
Parabolic.
parabolic. Greater than 1. Greater than 1 means what? It could be
An ellipse. That's it.
greater than 1. What is, if it says greater than 1, what does that mean? It could go up to?
Hyperbolic.
Okay. So E greater than 1 is hyperbolic, or E greater than 1 implies E could be infinity, and E could also be 0. Okay. So the range of this is from 0 to infinity. What Kepler observed was, what was the range of what Kepler's observation was?
What? He was either infinity.
What was the range of E for Kepler's observation?
1 to infinity.
Huh?
Greater than 1.
No, guys.
0 to 1. I mean 0 to infinity.
R.
Guys, listen to my question. Don't look at your cell phones. Okay? Sandra? E, according to this, is 0 to infinity. It could take any range. What was Kepler's range? What range does Kepler's? It's on the board.
0 to 0.
Huh?
0 to 1.
Yeah. Less, you have to say not 0 to 1. Keep in mind it is not
Greater
0
than 0
to 1.
and less than 1.
Yes. It's very specific. What does 0 to 1 include?
0 to 1.
What are the three? What does 0 to 1? What kind of orbits does 0 to 1 include?
Ellipse and what was the circle, ellipse.
Circle, ellipse, and parabol. Between 0 to 1, greater than 0 and less than 1 is ellipse. And Kepler only talks about elliptical orbits. With the, it also, it is not complete here. It says in an ellipse with the sun at not the center, again at one of the focus. So the center is different from the focus. Again, this is very, very important. What is the difference between center and focus? Can you draw an ellipse from the center?
No.
Where do you draw the ellipse from? How did I say you can draw this ellipse from?
When you say from the center,
I told you this, right? What do you know about ellipse?
it's not a perfect circle.
Okay.
That's straight stuff.
If you look at an ellipse,
It's like an oval.
huh?
It's like an oval.
What do you know about it? Do you know any characteristics of ellipse?
I know
This is the ellipse, okay?
the size of the tip of the
Huh?
the longest and the height.
What is this?
The horizontal distance.
No.
Equator.
Radius, you mean diameter?
This is a major axis.
Oh,
Do you remember?
Oh, what it's saying?
Major axis.
Major axis.
What is this?
Minor.
Line.
Where is the center?
In the middle.
The middle. The sun is not here.
No, it's all set.
You need to see me in my class, Jessica. See me in my office.
Oh.
When you're drawing the ellipse, this is where you keep your pegs.
Right.
Okay? and then you draw. So this is where the sun is. You understand? Now, the sun is not at the center.
It's opposite.
Huh?
It's at focus.
It's at the focus.
So does it roll between those 2 points? Is that what you're saying?
That will come back to later, but this is what he said.
Okay.
Observations. Okay. Again, strictly speaking, nothing is revolving around nothing. Okay. Strictly speaking, what did I say? Strictly speaking, when two objects are orbiting, what do they orbit around?
The center of
Huh?
Each other.
no, the center of gravity.
The center of gravity of the two systems.
Yeah.
Okay. But this sun being so huge, you can say if you take two systems, the center of gravity is almost at the center of the sun itself. And that's what Kepler observed. But if you look at Newton's this thing, you can say that they'll never orbit around one object never orbits around the other. Always two objects orbit around
Center of
with
gravity.
their center of gravity. Okay, so this is very important. This implication is very important. I'm going to ask you this in the exam.
On the test, do you want us like?
I may ask you, first you should know the trajectory equation, orbit equation, or
Kepler's first law.
Kepler's first law you should know that. And why Kepler's first law is a special case of this. Why is it a special case?
This is only the elliptical.
Only elliptical. You can explain saying the total range of E is 0 to infinity, but in Kepler's law, the range is only
Greater than 0, less than 1.
yes.
Hey.
Yeah, you're right. Okay.
The second law states that so when the orbiting body, or let me put it in terms of Kepler. What was Kepler talking about with regards to orbiting body? When he said orbiting body, he was only talking about planets.
Yes.
Okay? He only made his statement for
Fine.
planets. He didn't even include
Satellites.
moons because he didn't even
Yes,
include moons. Okay, he was only talking about planets. Did we even imagine about satellites during that time?
No.
When was this guy Kepler? Do you guys know?
Galileo, so
No, not this.
No, it's like maybe 11. Oh,
1600. Okay, 1600 AD.
Closer to BC.
Around 1600 and 1700 when Kepler and
But when was Galileo?
Galileo, all those guys were much before.
13.
So he says planets orbiting around Sun
1642.
trace equal areas
Come on, but I'm not talking about.
That's his
Galileo tried to prove
In-
that wrong, and he was wrong.
equal
Yeah, Galileo connected.
times.
So are you saying that he's right or wrong
What?
with the first statement?
His statement is correct.
Is it-
For all practical purposes, it is correct. Guys, pay attention here. The second one is planets orbiting around Sun trace equal areas in equal times. Okay, understand this statement now. Okay, now again I'm going to draw this ellipse. I'm going to draw.
So you're telling me in the time it takes for Earth to travel around the Sun, which is 365 and 1.2 something days, it would take Pluto the same amount of time to travel around the Sun.
No.
Distance.
This is not related to. So he doesn't really compare. He only compares two bodies. Okay, at a time. What that means is, now let's say the Sun is here, right? This is generally what we do is we call this as the focus, and this is the occupied focus, and this is the unoccupied focus. Why is this the occupied focus? That is what is occupied. What is here?
Just snap and grab.
Nothing. This is just space. You see that?
So
This
what-
point,
So what does that have to do with it?
but the ellipse, it's just unoccupied focus.
Okay.
Got it?
Like, what is it?
But yeah, like. I
It's a
understand.
point in space.
But like, why do you care about it?
Yeah.
You don't care about it.
So why are we running it?
We're talking about an ellipse. Okay? Otherwise, ellipse will not make sense
So why is it on the board?
for math.
It's right.
Your math. You cannot do math if you don't know this.
If you don't.
See, a lot of the orbit, although the orbit itself, what is an orbit?
What is the?
What is an orbit?
It's an investment fall, right?
Do you even see an orbit if you just look into space?
It's a pattern or a path.
Huh? You don't see it, right?
Yeah.
It is what everything is being traced. This line is being traced. You don't see it. Okay? This focus is there. You don't see it. This is there. You don't see it.
Okay, I see.
The math is all there. It's abstract, but you don't see it. You got it? So that is the reason I'll show you why this is important. Understand this. Let's say
Math is the universal language.
this is the area. This is T0. Okay? The Earth is here. Sun is here. Okay? Earth is here at time t equal to T0. It's here at time t equal to T1. You got it? It's going like this. Earth is going like this. Everybody with me?
True.
At time T0 it is here. Let's say. At time T1 it is here. At time T2 it is here. Okay. This is, let's say, what is this area? dA1. This area is dA2. You with me? This is the area of a sector. Everybody understands the area. What is the area of a sector? How do you calculate the area of a sector?
It's like,
You have to just apply area of triangle. Okay. The height is this, radius. R theta is the base.
one half, it's like,
1/2 height into R theta will give you the area. Now what second law states is dA1 divided by
DA2.
T1 minus T0 is equal to dA2 divided by T2 minus T1. This is equal to dA1 plus dA2 divided by anybody?
T2 minus T2 minus T9.
Yes.
Right.
You see what is happening?
Sir,
This area, so what happens is, if you're looking at this point, okay, now consider this point, and consider, let's say, t minus 1, and let's say this is t n, right? The area has to be the same. You agree? The area divided by time has to be the same.
Yeah.
What that means is, if it has to cover a certain area here, right? Now, can I say this area is equal to, let's say, this area?
well, just look at it, the time is the same.
Okay. Now, can I say almost this area is equal to this area?
Is the time the same?
Yeah, what's up?
Area is the same.
Okay.
It's better. It's better.
It's close.
Yeah, we're closer.
What is happening here? What is the area a function of? Area is a function of this, right? Plus this data.
Yeah.
So here this is smaller, this is bigger, right? This is bigger and this is smaller.
Yeah.
If these two areas are the same, according to this law, they have to take the same amount of time,
Yeah.
correct?
Yeah.
From this point to this point, it is going to take the same amount of time for the satellite. From this point to this point, it is going to take the same amount of time. What does that tell you? It's traveling much faster here than here. You see that? It's traveling much faster. It's traveling the fastest when it is the closest. It is traveling the slowest when it is the farthest. Okay? That is what it is saying. Do you see that?
Yes.
You see the implication of this. So dA by dt is what?
Constant.
Is constant. This dA by dt, which is constant, is h volt. What do you know about h? We discussed this yesterday.
Oh,
What do you know about h?
equal, it's a concentration of equal momentum.
What do you know about it?
It equals 0 and
We've been talking about this. You're not going to pass the
Oh, it's
midterm.
conserved or constant.
It is constant.
Yeah.
It is also conserved. H is also conserved.
I thought it was only.
Is 2
underlying.
conserved? Is 2 constant?
Yeah.
So this is constant, this is constant.
Cool.
Okay? So you see how it is conserved. It is all depends on the conservation of the conservation principle. What is H? R cross V, right? If V increases, what should happen to H? Now the product has to be the same, right? V increases. Here R decreases, right?
Yes.
Compared to this, R is the least. V has to be
Increasing.
the highest.
Yeah.
Here R is the
Highest.
highest. V has to be
The lowest.
the lowest. Conserve that. You got it?
Yes.
So lot of things, if you are trying to verify, you can simply blindfold yourself and say H has to be conserved. Let me check if it is conserved or not. If you're trying to verify your calculations. You see that?
Yes.
Okay. And the last principle or last law Kepler's third law. States that t square is proportional to
No, I was saying, I was saying, he said, I was shooting my coach, and I said, yeah, that's why he's not a goat. I said, Michael Jordan's good. I mean, Michael Jordan is over mechanics because the NBA is orbiting around Michael.
so the third law, which is the final law, it states the time period of an orbit or the square of the time period is proportional to what it says is, what is time period? What do you understand by time period?
How long it takes to make a complete
Complete orbit. Yes. So if you start from here, the time taken by Earth, what is the time period of Earth?
365.24
60.
something
Right.
days.
So 365 plus days.
How
Right.
many
So,
hours is that?
the time it takes is, so that is the reason if you look at it's 365 days plus. Okay. This time period is proportional to the mean distance. What do you understand by mean distance?
The mean, like the actual mathematical formula.
Mean distance in the context of an orbit. Why do we talk about mean distance?
You need
Anybody? Look at that and tell me what do you understand? Just look at it and just you should not be doing any other work.
Mean by average distance from the Earth and the Sun.
Is that an A?
Hmm.
It is.
Yeah.
Okay, thank
mean is what the number.
What do you understand by mean distance?
Mean
Or-
is average.
What is the distance? What do you understand by distance?
Average.
you. Distance is between A and B.
The R.
This, Jessica.
This is R.
Yeah, you asked about the distance.
R.
R is the distance, right?
R, okay.
What do you know about R?
It changes.
It changes.
Because it's an ellipse.
It changes, okay? It is changing. Here it is minimum, here it is maximum,
That's
right? That is the reason. So what is this mean distance now?
it's the average between the two.
Yeah.
Yes, sir. Yeah.
It's the same.
This is that A. What is this A? What do you call this A? It is the semi-major axis.
The semi.
This is the major axis, right?
So half.
So
Half of that is the semi-major axis.
Semi-major axis.
Okay.
Yeah, it's
This mean distance is equal to that semi-major axis. Now you see the importance of this?
Fun stuff.
I mean, to be honest with
Is this point in an orbit? What is this point in an orbit? This is the center, okay? Is this point in an orbit?
Is it?
What is this point in an orbit? It's just space, right? Free space.
Yes.
But this is that distance, mean distance.
Okay. So what is the other element telling me?
Huh?
What is the other element?
This distance. So now think about,
They're saying it's just another 8.
Yeah.
So basically the whole major axis is 2
is this some point of significance?
Yes.
What is of significance of this? Is there anything physical happening here?
Okay, no.
But it is important in the context of mathematics.
Mathematics.
Okay. So this becomes the, if you are talking about depending on, do you have to be in this orbit? What happens if you are in this orbit?
I mean,
So think about this, okay? The satellite, the orbiting body can be here or here. You understand?
Yeah.
Don't hum. Orbiting body can be either be here or here. When will your, let's say you launch a satellite, okay? If you want to go in this direction, farther in this direction, you put it in this ellipse.
Yeah.
If you want to go farther in this direction,
You go the other way.
you put it in this ellipse.
okay, so you can use each focus.
Right. So when you put something, these 2 points are not necessarily fixed. Okay. Only when you put something, this point becomes relevant. See that?
Yeah. Well, the whole satellite thing.
Huh?
If you launch it either way.
Yes, you can launch it either way.
So,
So when this point becomes occupied focus, if the push it in that direction. This point becomes the occupied focus if you push it in this direction.
Right.
Got it? So these points will be relevant. These points are not necessarily fixed. It depends on what orbit we are talking about. Yes.
So just to make sure I understand that, Everything you wrote right there, you could have wrote at the other.
Yes. So here it starts like this. Okay. Here is your Earth is like this, right?
Yeah.
You do this.
Higher learning.
Right.
This becomes the point.
Right.
Okay.
Real quick about the areas.
So this is your Earth, right? How do you launch? You go this. You go like this. Your rocket goes like this. And if you do this, it becomes this point. You got it?
Yeah.
If you do this, it depends on how you launch. There is nothing like orbit. It depends on how you push your satellite. You got it?
Right.
If you go here and you push it like this, it becomes this point.
No.
You got it?
Yeah.
It's not pre-existing satellite. It's not like this thing is here, the satellite. Depending on how you orbit it or how you launch it, it takes either of this.
But then, like, let's say you have like,
Can you even the other thing is, let me just finish this. You could even do this. Our convention is to use the anti-clockwise direction. Okay, we use generally this direction.
Is that preference?
It's convention, but the orbit can be prograde or retrograde. We always talk about prograde orbits. Prograde orbits are your Earth is spinning, right? If you orbit in the same direction, it's a prograde orbit. If your Earth is spinning like this, can you orbit like this?
yes,
You can orbit like this. That's a retrograde orbit. That retrograde orbit has a much less life. It will come down soon. So if you want to launch something in orbit and pull it down soon, you'll put it in the retrograde orbit. If you want it to be doing this, right? So have you experienced that? If you try to run against the wind, what happens? Right? So that gravity, depending on what direction you launch, again this orbit can shape. All this is covered in that one equation.
So does that matter for planets without like an atmosphere like our?
It matters. So it's not a function of atmosphere.
Okay.
You said if it goes the other way, it would come down faster.
Yes.
Why?
It's
Because
so
the
gravity.
gravitation
Gravity is
pull.
not friction.
That's almost stronger though, bro.
How's gravity strong? It's like pushing against the
We'll talk about that.
Alright, so
As well.
have you ever like rolled down like when the wind is blowing, bro, you just back into the wind?
Yes, just
So,
You can't even do that.
is that question you talk about lifespan?
Is
Is like circle longer than this, or is it all have like exact or lifespan? Or is there one that's more conservative than the other?
no. It's not. The shape itself is not going to affect the life. Okay. The direction of its this thing and the height is going to affect. So if you can put
think about it like a tornado, you know what I'm saying? If you try to run around the tornado, it's going to
Two
move
things.
this way.
For example,
But if you run with it, it's
two orbits of different shapes could have the same path.
Okay, just depends on like how far it is from the earth.
So that's an important question. So it's, what she asked is, pay attention here. We'll just wrap it up. Does shape have anything to do with the orbital period?
This is shape, yes.
Shape, that is not the shape, that is the direction. I am talking about direction. Shape, what do you mean by shape?
Shape of the planet.
Shape of the orbit.
Does that mean the orbit?
The time period, does the time period, listen to the question. Does the time period have any effect, or the shape of the orbit have any effect on the time period? The answer is on the board.
Yes. Yes, because of the distance it will have to cover.
Yeah, I mean,
Like, if that was a circle,
No.
Nope, it's
if that
all
was a
related.
circle, it will be a short distance to cover.
It's all related, bro.
This A, is it independent for shape?
No.
Is it shape dependent? What is this A for a circle?
exactly.
It's just a symmetry.
It's R, right?
Yeah.
For ellipse, it's just mean distance. As long as that R and mean distance is the same, it doesn't matter what shape you're in.
Oh, okay, cool.
Okay. It matters in the sense Now, when we talk about this, this discussion is limited to Keplerian orbits or Keplerian motion. Okay. So we don't talk about atmosphere. Okay. Now, if the A is the same for a circular orbit and an elliptical orbit, right? See, A is the same. Considering atmosphere, which one will degrade first?
I'm sorry, I don't know.
This A, you have two orbits, okay? Circle, ellipse. A is the same. Strictly speaking, the time period is the same for both of them. By this law, it is same, right?
Yes.
This law states that you take two orbits, circle and ellipse. The time period, as long as that A is the same for both of them, the time period is the same. In reality, you take those two orbits, which one will degrade fast?
Sir.
I'll say. Wouldn't the ellipse have to be faster?
Huh?
Wouldn't the ellipse or if you the same speed, same
With the same-
that's
Everybody
right.
lost there.
The elliptical orbit will degrade faster. Why so? So what happens? What is closer to the body? What do we experience?
Speed, yeah.
We experience, again, this. What I'm asking you is outside the context of this discussion. So answer in this thing. What do we experience closer to Earth? Friction or atmospheric drag. You see that? But we don't talk about atmospheric drag when we're talking about Keplerians. What is the assumption under which the two-body problem is derived? The assumption is gravity is the only force acting between the two bodies. It's the only external force. Right? We don't talk about atmosphere. But when atmosphere comes into play, so what will happen is, if you're talking about circle, so let's say this is the atmosphere, right? As long as the circle is outside the atmosphere, right?
It'll be the same.
It won't experience that. But if you look at ellipse, if you have to have the same ellipse, you have to go like this and go like this, right? So every time it comes into the atmosphere, it will be slowed down.
But the time will be the same.
So
Realistically, the time will not be same.
So the circle has less degradation with or without atmospheres and like included in the forces.
Huh?
Is it with or without atmospheres included? The atmosphere included in the forces. Like which scenario?
With the atmosphere, again, it's if you look at the circle, okay. If the circle itself is in the atmosphere,
It's gonna be slower.
it's going to be slow. You can have a match with a very low eccentricity or high eccentricity ellipse, which will go like this. So if the circle, let's say this is a circle, okay,
It's gonna be
So
slower.
we're not.
and this is the atmosphere.
We're not.
Now what you can do is you can have an A with something like this. You see that? So that time this will degrade slower. Now when we want to go close towards sun, we take this extremely high elliptical orbit. You see that?
Yes.
This is the only way we can go close to the sun. Right? If we went to the sun in a circular orbit, what will happen?
Burn out.
Hmm?
It'll burn out.
It will burn out, or we won't be able to communicate, right? So what this can do is, it will go here, okay? It will take some data from the sun, and it may not be able to communicate effectively from here to here. But when it comes back, when it is here, much closer to Earth, it will send that signal, all that data.
Yeah.
So this highly elliptical orbit called the Molniya orbit was invented by the Russians. Very useful orbit. So what we'll do is, I want half an hour time tomorrow. When can you, even if it's just a few of you all, that's okay. I can upload the lecture online. So what we'll do is, tomorrow's lecture will be your portion for midterm. I'll only talk about the different orbits, different shapes of the orbit. For this test, there will be no derivations. I won't give you any derivations. Okay?
So no math, just words, no math.
No, he said no derivations.
I'll give you two problems from the first part of the vectors and thing. Two problems. One will be related to the projection problem. I don't think everybody got the projection problem right. Projection concept.
Okay.
One problem on projection, scalar projection. Okay. One problem to test your cross product and dot product knowledge.
Okay. So you won't have to worry about Kepler's law for two-body problem.
No, that is from the first. You have to work about this. So I'm saying
Oh, that's what's going to be from the first.
part.
Okay.
Two problems from the first part. One is scalar projection. Okay, understand scalar projection. I'll give you an easy problem, but it will not be exactly what has been given in the assignment or your exam. I want you to think. It will be relatively simple. Okay, understand projections. It could be as simple as find the projection of A on B. I won't give you the formula for projection.
Okay.
Second one is understanding. I want to test your understanding of cross and dot product. It will be a simple problem of dot and cross product. Does that make sense?
Yes.
These two problems, the 4 formulas I wrote yesterday. You see that? You remember I summarized what we have done until now, the review part. Go back and review the lecture. I think that is better.
Okay.
Okay, because it's not just a formula. I want you to review that portion. I will not ask you derivations, but there will be problems. Yes, you have to know which formula to use.
Do you mean the two-body problem statement, the solution to two-body problem?
Yes,
These
all that.
should be the equation and concept.
Correct. Okay, I might ask you, explain why angular momentum is conserved, or how do you. So today I talked about this, right? So this itself means that angular momentum is conserved, as long as the plane is the same and it is doing the same thing. Okay. So if this, what happens? So this is the angular momentum vector. Okay. What happens if the direction changes?
The motion is changed.
The plane changes. Okay. What happens if the length changes? This will become bigger
If the length increases.
if the length increases.
Okay.
You got it? If the length of if the magnitude of the vector, so you're talking about angular momentum vector. Vector has two quantities, right? One is magnitude, the other is direction. If the direction changes, the plane itself changes. Okay? If the magnitude changes, the size changes. If the magnitude decreases, it will become smaller.
Yeah.
If the magnitude increases, it will become bigger. Does this become bigger or smaller for Earth?
No.
It doesn't. So this has to be
The same.
same. It is constant. So that way I test your understanding of conservation of angular momentum. Okay?
Yes.
And I want you to, so those 4 formulas, Kepler's 3 laws. Memorize the Kepler's 3 laws.
Okay.
And what we talk about tomorrow. I'll talk about the different orbits. I want you to be able to draw orbits.
What time are we meeting tomorrow?
Huh?
What time are we meeting?
What time are you guys available?
12 to,
Most of you, tell me, give me
1:30.
12 to 1:30. Does that work? So let's do at 12. Okay. How many of y'all, whoever is available, just come. If you're not available, just go and watch the video lecture. Is that okay?
Yes.
And we'll have, the test will be based on what we cover and do.
An hour.